Welcome everyone to the next Gen 4 International Forum webinar presentation. Today's presentation on directed energy deposition process of corrosion-resistant coating for lead, bismuth, eutectic environment. Doing the introduction today is Dr. Patricia Pavier. Patricia is the chair of the Gen 4 International Forum Education and Training Working Group. She's also the National Technical Director of the Molten Salt Reactor Program for the Department of Energy in the United States under the Office of Nuclear Energy. Patricia.
Good morning. Thank you very much, Berta. Good evening, everyone. It's a pleasure to have with us today Dr. Gi-Dong Kim, who is the popular vote winner of the 2023 Pitch Your Research competition. Dr. Kim is a senior researcher at the Korea Institute of Material Science. He earned his master in material science and engineering from Pusan National University in the Republic of Korea, and he has also a PhD in nuclear engineering from Ulsan National Institute of Science and Technology. His research interests include additive manufacturing, brazing, and the development of welding procedure for industrial application. He's also working as an authorized nuclear inspector to ensure the safety of nuclear power plants in Korea. Recently, he has been conducting research on advanced manufacturing technologies applicable to small modular reactor, including laser-directed energy deposition and powder metallurgy, hot isostatic pressing. So without any delay, Dr. Kim, I give you the floor. I thank you very much for volunteering to present this webinar. Thank you.
Thank you, Patricia. Good morning, good afternoon, and good evening, everyone. I am Gi-Dong Kim from the Korea Institute of Material Science. First of all, I'm very honored to have the opportunity to present at the Gen 4 webinar. The topic of my presentation today is a directly energy deposition process of corrosion-resistant coating for lead bismuth eutectic environment. My presentation consists of 5 chapters, as shown as this slide. Let's start with the introduction. This picture shows the various generations of nuclear reactors. Among them, current nuclear power plants use Generation 3 type reactors. Generation 3 Plus and 4 reactors, which have improved and innovative designs, are usually small modular type and widely developed by many countries, including the Republic of Korea. Especially, Gen 4 reactors use not only light water, but also various materials such as inert gas, lead, molten salt, and sodium as a reactor coolant. The Generation 3 or 3 Plus reactor using a thermal neutron with an energy level of 0.025 electron volt uses 235 uranium as fuel, which was an isotope that accounts for only 0.7% of the total uranium in nature. So it was not easy to see it as an abundant resource. In addition, after the fission reaction, a large amount of high-level radioactive waste composed of long-lived fission products and minor actinides was generated, which has been a dangerous radioactive material for tens of thousands of years. Most Generation 4 reactors are called fast reactors because of the high energy level of neutrons. High energy neutrons can transform the 238 uranium into fissile isotopes such as 238 plutonium. This phenomenon is called breeding, and this kind of reactor is known as breeder reactor or fast breeder. Moreover, fast reactors generate short-lived waste, unlike light water reactors that use thermal neutrons. The comparison of nuclear waste radiotoxicity after transmutation is shown this figure. This figure represents that fission products produced in fast reactors reduce their radiotoxicity, like uranium ore, within 300 years. Therefore, fast reactors can make nuclear power essentially a sustainable and renewable energy source. There are three types of reactors considered the most promising for practical application among the various SMRs designed in the Republic of Korea. First, ISMR, which is a Generation 3 plus light water reactor aimed at power production. This model is an improved version of previously developed SMART and has been under development since 2023 with a financial support from the government and KHNP. Next, micro-Uranus, a micromodular reactor that uses lead bismuth eutectic as a coolant. This reactor completed its conceptual design in 2022 with government funding and is being developed for practical application. Its primary purposes are power production and marine application. Lastly, the molten salt reactor, which has been under development since 2023 with financial support from the government and shipbuilding companies. This reactor is designed for marine application, and its conceptual design is currently in progress. This slide presents important information on the necessity of developing the nuclear-powered reactors for marine applications. The IMO currently strongly requires reducing the carbon intensity of all ships by 40% by 2030 compared to 2008. However, most ships are currently unable to meet these regulations. Therefore, there is a growing need for nuclear propulsion ships. Historically, nuclear-powered submarines and aircraft carriers have been built and operated with compact and modular designs developed to fit their limited spaces. Additionally, since 2019, an icebreaker equipped with two PWR-type MMRs has been in operation. Some refer to it as the nuclear Titanic or Chernobyl on ice, opposing its use. But it is crucial to widely promote the passive or inherent safety features of SMRs because it can automatically shut down without external power and human operation. This table summarizes the key parameters and materials of Generation 3 and 4 reactors. The widely constructed PWR and BWR types operate at relatively lower temperatures and neutron energy levels, making them suitable for using materials that are commonly used in the current industry. However, for the Generation 4 reactors listed below, the diverse types of coolants, high temperatures, and neutron energy environments require the use of specialized or new materials. This table shows the basic characteristics of selected reactor coolants. Among them, lead bismuth eutectic is efficient for fuel breeding due to its limited neutron modulation and absorption characteristics. Additionally, its good thermal conductivity enables the production of compact, power-dense cores. Furthermore, its high boiling point, chemical stability with air and water, and ability to remove decay heat through the natural convection in accidental conditions provide inherent safety features. Thus, LBE is one of the suitable SMR coolant material. There are several candidate materials for structure and fuel cladding in liquid LBE-cooled reactors. Firstly, there are ferritic martensitic steels that have BCC crystal structure. The material has good mechanical properties at elevated temperatures, excellent resistance to void swelling, or low ductile to brittle transition temperature, and moderate corrosion resistance due to chromium contents. However, it is reported to be susceptible to liquid metal embrittlement. Secondly, there are austenitic stainless steels with FCC crystal structure, which exhibit good performance at relatively low operation temperatures. However, irradiation-induced void swelling could occur at high irradiation doses, and there are issues with liquid metal corrosion. Other materials with superior properties are also being considered, but their manufacturing process and reliability need to be verified. The previously introduced candidate materials in LFR are not fully compatible with high-temperature liquid LBE coolants. Major degradation phenomena in LFR materials can be broadly divided into two categories. The first is liquid metal corrosion, represented by the selective leaching of nickel. In a liquid LBE environment, forming a stable oxide layer that provides corrosion resistance can be achieved through alloying elements in candidate materials or surface coating on structural materials. For this, active oxygen control is essential. The second is liquid metal embrittlement, where ferritic steels are more vulnerable than austenitic steels. However, the mechanism of LME is not clearly revealed. The major alloying elements in steel are silicon, aluminum, titanium, niobium, and chromium. These elements show protective results in an LBE environment. Among them, chrome, silicon, aluminum are the most effective elements, as shown in the Ellingham diagram. First, chrome contents should not exceed 12%, as higher levels may cause integral corrosion and weaken the alloy. Second, silicon contents should not exceed 2.5%. If the silicon content is over 2.5%, the steel could become susceptible to radiation embrittlement. Third, the aluminum content should be over 5.5%. Theoretical calculations indicate that a minimum of 5.5% aluminum is needed to produce an aluminum oxide layer. However, high aluminum contents can cause low weldability and castability and may lead to hydrogen embrittlement. The following are several representative LMC resistant materials developed by other researchers. Alumina forming austenite includes chrome, aluminum, and titanium as corrosion-resistant elements and has an FCC structure, providing good compatibility with austenitic base metal. However, there is a concern about selective nickel dissolution due to its nickel content. The iron chrome silicon system includes chrome and silicon as corrosion-resistant elements and has a BCC structure with high strength, but there is a concern about irradiation enrichment. The iron chrome aluminum system includes chrome and aluminum as corrosion-resistant element, as a BCC structure with good corrosion resistance, but its weldability needs to be verified. The development of these LMC-resistant materials has two significant challenges. Firstly, there are limitations in the manufacturing process. It is extremely difficult to produce dual-layered tube with the final desired shape using conventional methods such as extrusion, figuring, and casting. Secondly, these materials are not listed or approved for use in ASME or CAPLI codes, making it impossible to use them as a single metal tube. Now, I will explain the approach and objectives of this study. According to the requirements that materials not listed in the ASME code cannot be used as pressure retaining materials, but there is an exception. Unregistered material can also be used if the clad material has 10% or less thickness compared to the base metal. Additionally, we have focused on the rapidly advancing metal additive manufacturing technology. The two representative metal additive manufacturing technologies are powder bed fusion and directed energy deposition. Here is a general comparison table of these two technologies for reference. Actually, these specifications are improving with technical advancement. This video has been sourced to help you understand the two metal additive manufacturing technologies. Among these, for accurate surface coating of metal AM on existing material, the DED process can be selected. In addition to the metal AM shown in the previous slide, there are various surface coating processes available. Representative methods include CVD and PVD, electroplating and electrolysis plating, and spraying processes such as cold spray and thermal spray. Although these processes are already applied in the industry, they have limitations when it comes to applying them to multi-layer metal deposition, which is the focus of this study. Summarizing the previously shown information, the method I have derived for the development of materials for Gen 4 reactor applications can be outlined as follows. Generation 3 reactors use existing materials and manufacturing technologies listed in the code and can be used well. For Generation 4 reactors using various coolants, the development of new materials suitable for the coolant and operating environment is essential. However, to overcome the technical barriers related to the code registration and post-processing of the materials to their final dimensions, it is necessary to employ surface coating of 10% or less thickness of the base metal and optimize the parameters of the DED process to enable a thin coated layer. Therefore, the objective of this study is to examine LMC resistance clad materials manufactured by the DED process, propose optimized DED parameters, and report the evaluation results. From this slide, I will explain the experimental procedures. Since existing DED equipment is not sufficient for the fuel cladding dimension, minimum 1 meter long tube, we newly designed the DED equipment as shown in this slide. This table shows the detailed specifications of the newly designed DED equipment. Since the purpose of the device is to apply zinc coatings, a 1 kilowatt laser source was selected. Additionally, it is designed to use CAD files in STL format or to specify variables according to the applied shape. This photo shows the outlook and deposition process of the DED equipment. To perform the DED process, suitable metal powder is required. The previously introduced LMC-resistant materials are not commercial materials and are not listed in any codes. Therefore, alloy billets were custom manufactured and metal powder of the appropriate diameter was produced through the gas atomizing process. In this study, AFA and iron chrome silicon alloys were manufactured into powder form. For the comparison group, commercial STS316L powder was used. These powders were characterized for their flowability and confirmed to be suitable for the DED process. Firstly, we performed DED parameter optimization for the combination of the newly designed DED equipment and the manufactured metal powders. Through preliminary experiment, we selected 9 conditions with laser power and laser scan speed as the main variables. The DED coated layers were characterized through microstructure observation, mechanical testing, and corrosion property evaluation, including high temperature LBE exposure test. The detailed result of these experiments are documented in the referenced research article. From this slide, I will present the experimental results. To determine the optimal heat input conditions for the laser DED process, single-line experiments were performed, and the cross-sections were observed. As a result, the dilution width and height of the single-line clad were measured. In this study, low dilution is preferred. When fabricating dual-layer coated materials, processing conditions with low laser power are advantageous, considering the bead size and dilution rate, because the layer thickness will probably be limited. Therefore, it is determined that the process condition of specimen 4 and 7, where the single line clad width, height, and penetrate depths are relatively small, are selected as the optimal conditions. However, in the process conditions of specimen 7, because the laser transfer speed is the fastest under the lowest laser power condition, the bonding strength is expected to be weak, so it was excluded from the optimal process conditions. Therefore, regardless of the powder type, the optimal process condition for producing a single line clad is laser power of 0.4 kilowatt and a laser transfer speed of 14 millimeter per second. To understand the component behavior of the single line bead, EPMA line analysis was performed. It was found that under all conditions, the composition distribution of AFA is similar to that of the substrate material 316L. On the other hand, in case of iron chrome silicon, differences from the substrate composition were expected, but differential components distribution was observed even within the melt pool. In particular, the dilution of nickel, which was present in the base material, was observed locally. The variables used for parameter optimization were also applied to the surface coating. The deposition was performed using a zigzag pattern with 2 layers rotated 90 degrees. Visually, the coated surface shows a line remaining morphology. The surface of the deposited layer was analyzed using XRD. As expected, the substrate STS316L layer and AFA layer showed the FCC austenitic phase. Additionally, the iron chrome silicon layer exhibited the BCC ferritic meltensity phase. To select the optimal parameters, the cross-section of the surface-coated layer was observed. Similar to the single-line analysis, considering the dilution and layer thickness, condition 4 was determined to be the most suitable. For the AFA coated layer and iron chrome silicon coated layer, the optimal parameter was determined to be the same. Also, the EPMA mapping results were similar to those of the single line analysis. The composition line analysis results for each material under the selected conditions are as follows. STS316L and AFA showed almost the same composition throughout the layers. For iron chrome silicon, the first layer showed an irregular composition distribution, while the second layer showed a relatively constant composition. To investigate the phase transformation behavior under the selected conditions, EBSD analysis was performed. Consistent with the XRD analysis results, AFA exhibited an FCC structure, while iron chrome silicon exhibited a BCC structure. Additionally, it was observed that the first layer had high deformation and dislocation density, whereas the second layer has relatively lower deformation and dislocation density. To determine the hardness distribution of the coated layers, a Bicker's hardness test was performed. STS316L and AFA showed similar hardness throughout the layers, including the substrate. But iron chrome silicon exhibited hardness values over 400 HB. Since the developed materials may be exposed to high temperature environments, tensile tests were conducted at room temperature 300 degrees C, 600 degrees C to determine their strength. To prepare the high temperature tensile test specimens from the deposited parts, samples with a thickness of more than 4 mm were fabricated, and test specimens were extracted from the deposited sections. For STS316L and AFA, the result at 600 degrees C showed lower tensile strength and higher elongation compared to the result at 300 degrees C. For iron chrome silicon, there was a significant drop in tensile strength at 600 degrees C, but elongation recovery was observed. To identify the cause of the reduced elongation, the fracture surface of the 300°C specimen was examined. The fracture surface showed a mixture of dimples and cleavage, and large aluminum oxide were observed in some regions. These aluminum-rich faces were calculated to have higher mass fraction at 300°C compared to 600°C. It is believed that these oxides act as crack initiation sites, leading to the reduction in elongation. The fracture surface of 300°C specimen of the iron chrome silicon coated layer was also examined. Similarly, large silicon oxides were observed, which also acted as crack initiation sites, leading to a reduction of elongation. For the comparison of the general corrosion behavior of each deposited layer, potential dynamic polarization test in 0.5 mole H2SO4 solution was conducted, and taper fitting results are enlisted in this table. Based on the result for corrosion potential and corrosion current density and corrosion rate, the iron chrome silicon coated layer demonstrated the highest corrosion resistance. Additionally, when considering the passive film breakaway potential, iron chrome silicon was determined to have the most stable passive film. Each coated material was evaluated for LBE corrosion resistance in high temperature LBE environment with controlled oxygen concentration. The samples were exposed for 500 hours and 2000 hours. After testing, XRD and TEM EDS analysis were performed to evaluate the oxide layer on the coated surface. This graph shows the surface XRD analysis of specimens exposed for 2000 hours. Due to the proper maintenance of oxygen concentration, various oxides were identified on the surface. Overall, similar surface phase constitutions as coated materials were observed. The AFA coated layer forms an oxide layer with an outer composition of iron oxide and iron chrome oxide, an inner layer of thin and dense aluminum oxide, which leads to a higher corrosion resistance by preventing oxygen penetration and metal dissolution. The iron chrome silicon coated layer forms an oxide layer with an outer composition of chrome oxide and iron oxide, and inner layer of thin and dense silicon oxide, which leads to higher corrosion resistance. Compared with the previous LBE exposure test results performed by other researchers on bulk materials, the DED coated layer shows very thin oxide layers for all powders. Therefore, the oxide layers of DED coated layer could have more protective in a high temperature LBE environment than bulk materials, leading to a longer material life. Now we move on to the conclusion part. Based on the experimental results presented previously, optimized DED parameters, including powder requirements, were suggested for defect-free and restricted base metal dilution. The results obtained so far are meaningful as they were achieved using plate substrate. However, they differ from the process of coating the outer surface of a tube, which is the ultimate goal of this study. Therefore, to achieve this final objective, we have developed a rotating fixture of tube coating enable a final coating length of 1 meter on the outer surface of the tube. Although the selected coating conditions for the plate substrate were used as a reference, additional parameter optimization was performed for tube coating to account for potential differences in cooling rates. The main variables were laser output, overlay ratio, and laser beam defocus. Due to the thin wall thickness of the tube, a laser power of 0.35 kilowatts was selected, while the other conditions remained the same as previously established. This video shows the process of coating an LBE corrosion-resistant material onto a tube of the finite dimensions. Through this, I have verified the feasibility of building a thin surface coating of LBE corrosion-resistant materials on the final size of fuel cladding using a rotating tube DED process with optimized process variables. To match the target surface roughness and coating thickness, subsequent surface machining on the as-cladded surface can be performed. In this case, as shown in the right-hand image, an improved surface finish and thinner coated layer can be achieved. The summary is as printed so far. For the future practical application of this process to SMRs, more diverse evaluation data is needed. Efforts are also required for the code registration of the developed materials, and additional high-temperature LBE experiments will be necessary to assess the lifespan of the coated layer. Lastly, our research team is currently working on developing the methodology for inner coating. I will conclude my presentation with the introduction of upcoming webinars. Thank you very much for your attention.
Thank you, Jidong. While questions are coming in, we'll take a quick look at the upcoming webinar presentations in July, online monitoring development in support of the nuclear fuel cycle, and in August, international molten salt research in support of the MSR development. And with my apologies, I should have removed the September presentation. That is still tentative. Let me, are you planning to conduct additional tests at different, that is, higher oxygen concentrations?
From the reference, the oxygen content is a kind of fixed concentration with 0.-7%. So I think the oxygen concentration cannot be a variable on high temperature LBE experiments.
Thank you. That's the only list of questions so far. If you have questions, please go ahead and we'll just wait a couple of minutes to see if there's follow-up to that or additional questions that people have of the presenter. In the meantime, I do want to say congratulations again, Jidong, for being selected the award and the honor from the Picture Research Competition. The future in the nuclear industry with the upcoming generation looks very promising with people like yourself and the expertise that you're developing and the talent that you show. And it's a pleasure to have had you today.
Thank you very much.
I don't see any additional questions. Patricia, do you have any? Oh, here's.
Okay.
The slides, yes, the slides are available. You can get them from the handouts pane now, and we will post the PDF on the GIF website at www.gif- I can't do it without the slide in front of me. The GIF website.
It's www.gen-4.org.
Thank you.
Okay, so there's no question, Bertrand?
That's all the questions I see.
Okay. This is fine. Everyone knows the email of Dr. Kim, so feel free to contact him directly. Again, thank you very much, Gidong, for the very interesting presentation. And like Bertha said, congratulations on being one of the winners of the 2023 Pitch Your Gen 4 Research Competition. I will launch the 2025 Pitch Your Gen 4 Research Competition on the 1st of October. So I will advertise through LinkedIn and different other platforms. So feel free to start looking at research for PhD, postdoc, and junior researcher. So with that, thank you very much, Bertha. Thank you so much again, Dr. Kim, and goodbye, everyone.
Thank you. Thank you again.
Okay, bye-bye.
Bye-bye.